Hi everyone, good morning. This is CP Prashant from KV Ganeshk in Pune. In the previous class, we were discussing about electrochemistry. We had done the redox potentials, the working of a cell, the Daniel cell, a representation of cell and things like that. And today in our class, we will be discussing about three very important aspects of electrochemistry. One, what if the cell is not in standard condition? In that case, what will be its voltage? The second aspect we will be discussing about today would be the conductivity of solutions, and the last aspect is about electrolysis. So we'll start with this particular concept. Suppose a cell is not in a standard state. How will we know the voltage of it? Let's take the same Daniel cell which we had discussed in the last class. I have set up a cell like this with zinc as anode, copper as cathode. It is not in the standard state. The temperature is different from 25 degrees Celsius. Pressure is different from 1 atmosphere. And the concentration is also different from 1 molar. This electrode is at 2 molar. This electrode is at 3 molar. What will be the voltage generated by this cell? Is it going to be 1.1 volt or will it be different? Obviously, when the electrode is not in the standard states, you cannot take the electrode potentials which are given in the electrochemical series, because the potentials given in the electrochemical series are standard reduction potentials. Right now, the cell is not under standard conditions. So obviously, the EMF of the cell cannot be calculated using EMF from the electrochemical cell because it is not under standard conditions. So under such circumstance, what do we do? A German scientist called Nernst, he studied about such cells and he came out with a formula which will help us to find out voltage of a cell when it is not under standard conditions. Let's consider the reduction of zinc 2 plus ion. Even if in this particular cell zinc is getting oxidized, please note, we have written the reduction reaction of zinc. Nernst has derived a formula E of this particular electrode, which can be written as E Zn plus Zn. Please note this E is not E0 because this is not under standard conditions. According to Nernst, this E should be E0 minus 2.303 RT divided by N into F log of 1 by concentration of Zn 2 plus. I will explain each term given in the formula. As you know, E is EMF of this particular electrode if it is not in the standard state. E0 represents EMF of the electrode in the standard state, which value we already know. R is gas constant, T is temperature in Kelvin, N is number of electrons which are involved in the reaction, F is Faraday, and this is concentration of Zn 2 plus. So what it means is this EMF of the cell, it depends on so many factors, not only the concentration. It depends on concentration, it depends on the temperature, it depends on the number of electrons involved. The same way, we can write the reduction of the other half this would give you copper metal. By the same expression we can write E of Cu2 plus Cu is equal to E0 of same Cu2 plus Cu minus 2.303 RT divided by NF log of 1 by Cu2 plus. So these are the reduction potential values of two half cells. We need to calculate, we need to find out EMF of the cell. As we have already discussed, as we already understood, EMF of any cell is EMF of right minus EMF of left. Therefore, we write EMF of this cell would be EMF of the right, which is reduction part, minus EMF of left, which is oxidation half. Note that this is not the EMF of a cell under standard conditions. So we are going to substitute the EMF of reduction, which is given by Nernst equation, EMF of EMF of reduction, and EMF of oxidation. So let's substitute the values here. EMF of reduction half in this particular case is the Cu2 plus Cu electrode, which is on the right hand side. So we substitute E0 of Cu2 plus Cu minus 2.303 RT divided by NF log of 1 by Cu2 plus. We have substituted EMF of the reduction half. Now let's substitute EMF of the oxidation half also, which is of zinc. So we write E0 of Zn2 plus Zn minus 2.303 R T divided by NF log of 1 by Zn2 plus. Since 2.303 being a constant, R being a constant, let's consider this temperature 25 degrees Celsius. If you conduct the cell or you set up a cell in the atmospheric temperature, and F is 96,500 coulombs, we can work out 2.303 R T by F. It will come out to be E0 Cu2 plus Cu minus 0.0591 divided by N log of 1 by Cu2 plus minus E0 Zn2 plus Zn. This minus with this minus will become plus. So it will be 0.0591 divided by N log of 1 by Zn2 plus. Let's simplify this expression. We can take E0 of Zn2 plus E0 of Cu2 plus Cu and E0 of Zn2 plus Zn together. So E of cell will be E0 of this part minus this part, E0 of Cu2 plus Cu minus E0 of Zn2 plus Zn. Now we have this part and this part. As you can see, this is plus 0.0591 by N. This is minus 0.0591 by N. Suppose I write minus 0.0591 by N. Log of 1 by Cu2 plus 0.0591 by N log of 1 by Zn2 plus. As you can see, this term is same on both the expressions, and this value we already know because this is E0 of the cell, because E0 of the cell is E0 of Cu2 plus Cu minus E0 of Zn2 plus Zn, whose value comes to be 1.1, So if you take this as constant 0.0591 divided by n, a common term from both the expressions. So this comes out to be log of 1 by Cu2 plus, since minus is outside, this will become minus log of 1 by Zn2 plus, which can be written as 1.1 minus 0.0591 divided by n log of minus of log 1 by Zn2 plus becomes plus of log Zn2 plus. So instead of writing this minus log 1 by Zn2 plus, the Zn2 plus comes in the numerator. So it becomes log of Zn2 plus on the numerator, and Cu2 plus is already in the denominator, which is minus, so it comes here Cu2 plus. This is the E of the cell, which is not under standard conditions. We need the EMF of the cell under standard conditions, which is 1.1. N is 2 in this case, because 2 electrons are involved in the process. On the numerator, you have Zn2 plus ions. In the denominator, we have Cu2 plus ions, which means the EMF of the cell is directly proportional to concentration of Cu2 plus, inversely proportional to concentration of Zn2 plus. Reason is there is a negative sign here. So EMF of the cell is dependent on the concentrations. So by changing the concentrations, the EMF of a cell can be varied. So this 1.1 is valid only when your cell is under standard conditions. The moment it is in not standard conditions, we will have to use the Nernst equation to find out EMF of the cell. Now let us discuss about a cell where number of electrons is not same in both the halves. Now let us discuss about a cell which is set up something like this: Ni2 plus, Ag plus Ag. Now in this particular case, you can note the number of electrons in the case of nickel is 2, because the oxidation number of nickel is plus 2, and the number of electrons in the case of Ag plus 1 electron is 1, which means when you write the Nernst equation, this N is not same for both the half cells. So let us write the equation of this reaction first of all. This equation of this reaction would be Ni plus Ag plus gives Ni2 plus Ag. To make the number of electrons same, you multiply this with 2. So Ni plus 2 Ag plus, it's giving you Ni plus 2 Ag. From the equation, if you try to write the Nernst equation, you will never go wrong. So my suggestion is, before writing the Nernst equation from the representation of a cell, it is better to write the Nernst equation from the equation of a cell. So let's see how you write the equation. E of cell would be E0 of cell minus 0.0591 divided by. Now what you do, number of electrons involved here is 2. But if you look at the half reactions, in the case of silver, it comes to be just 1 electron. In the case of nickel, it comes to be 2 electrons. So when you multiply this with the 2, it becomes 2 electrons. So what we made is, number of electrons is made same. So we can substitute this 2 here. But when you write the concentration terms, on the numerator, it is the electrode which is getting oxidized. That also happens to be the product in the equation. Look at Daniel cell, zinc plus Cu2 plus gives zinc 2 plus Cu. You can see zinc is getting oxidized. The Zn2 plus happens to be the product also. So when you write the Nernst equation. On the numerator, it is the product. On the denominator, it is the reactant. So, by the same logic, it will come Na2 plus here, because Na2 plus is the product, and Na2 plus also is the metal which is getting oxidized. And in the denominator, you have Ag plus, but it will be Ag plus square, because we have taken 2 common, so that the number of electrons involved becomes same. So when you write a Nernst equation, I think the best way, I suggest you, this is how it's better to write the Nernst equations. We will try to solve a numerical based on this. We have a cell which is set up something like this, CO2 plus, Fe2 plus, Fe. Let's say this cell is not under standard states, which means concentration of CO2 plus, let's say it is 0.5 molar, Fe2 plus, let's say it is 0.25 molar. For the question is this, you have to verify whether this particular reaction is possible or not, which means is this cell, if you set up like this, will it work or not, which means you have to see whether it is spontaneous or not. So what you do, you have to take the E0 values of both the half cells from the electrochemical cell. The E0 value of cobalt is minus 0.28, E0 value of Fe2 plus Fe is minus 0.44 volts. So first we have to see whether this reaction is possible or not. For that, what you do, find out E0 of the cell, assuming that this cell is under standard states or not, by taking E0 of the reduction minus E0 of the oxidation, E0 of right minus E0 of left. Now the reduction, as you can see, is this part, which is written on the right hand side. The value of EMF in the standard state is minus 0.44. Now we substitute the value of oxidation, which is happening here, it is minus 0.28. This comes to be minus 0.44 plus 0.28. The value you are getting is minus 0.16 volts. The EMF of the cell comes out to be minus. Now what information you get from this is,